So good morning, everyone. My name is Fernando, and I will be your lecturer for this special relativity, which is a Part B course in the direction of theoretical physics, basically. Now, I will start this course by explaining you what the title means, what special relativity means. So the first important point is that special relativity is not special, okay? Now, when you want to make someone feel nice, you tell them that they are special, and that's a very nice thing. For a physical theory, it's not a nice thing, okay? Because for a physical theory, it would mean that the theory applies only to very special situations, and this is not the case with special relativity, okay? So special relativity is a theory that describes the real world. All of it, all right? The second important point about this, so the reason why we use the word special sometimes is as opposed to general relativity, where in general relativity we consider gravity, and in special relativity we do not, okay? So that's the only reason why we use the word special. The second important point is that the word relative does not mean everything is relative, but actually quite the opposite. But special relativity will tell us what is relative and what is absolute, okay? When you describe a physical theory. And actually, understanding these sort of questions, so what is relative and what is absolute, will change completely, will transform our understanding of space and time. And actually, special relativity has had a bigger impact in our understanding of the physical world more than any other theory of theoretical physics. I would say maybe quantum mechanics is as big, and indeed, special and general relativity and quantum mechanics are the two basic pillars of theoretical physics, of modern theoretical physics, okay? It is quite sad / impressive / exciting that we don't know yet how to put these two things together, okay? But okay, maybe you do this next year or in your future. But basically this, special relativity, is one of the two pillars of theoretical physics. And the course will be organized as follows. Today, in the rest of today, we will remind some aspects of Newtonian mechanics, and these are basically things that you have already seen on the first 2 years here at Oxford, but we will revise some of the preconceptions and assumptions that are actually quite important, and you assume that they are true, and people has assumed that they are true over, hundreds and hundreds of years. And then, in the second part of the course, or the second section, we will see that we need to go from this point of view of Galileo and Newton to a new point of view due to Einstein. Because we will see, we will kind of describe experimental evidence that will tell us that some of our assumptions, when we describe Newtonian mechanics, are actually to be revised, okay, in a very fundamental way. And I am talking about really fundamental assumptions. Then we will start describing special relativity, or the special theory of relativity proper. And we will start with 1 + 1 dimensions. And I want you to start getting used to this notation. Here, the first one is a time direction, so it's what time it is, etc. The second one is a space, okay? So we assume that there is only one spatial direction and one time direction. And then we will see some of the nice implications of special relativity in astrophysics, astronomy, and cosmology, okay? Then we will have the tools to have a look at 4-dimensional and here we mean 1 spatial time direction and 3 space directions, space-time, and then we will see relativistic kinematics and collisions. Now, a problem that you are very used to in Newtonian mechanics is if you go to play snooker here in the UK, you learn how to use the laws of Newton, etc., to predict what happens with little balls. But in a special relativity, the world is a bit different. So we will see what happens with little balls in special relativity, right? Or rather particles at particle accelerators. So here we will see some particle physics, something quite cool actually. And then we will end up with something called relativistic electrodynamics. All right. If you have any questions at any points in the course, in the lectures, please feel free to stop me and ask me if something is not clear, okay? And I will also stay outside after the lectures for as long as you want, okay? So please feel free to stop me. Let's make this a very informal discussion. And do you have any questions up to now so far? Fantastic. Beautiful. So let's start then revising some of the things that we have learned in Newtonian mechanics. And what will be important for us is to revise the concept of relativity in Newtonian mechanics. The first thing that you learn in Newtonian mechanics is that in order to describe the motion of a particle, you need to choose a reference frame, okay? So I can have a description of a particle, you may have another description of the same particle, and our descriptions may be different, but they are equally good, okay? If we are reasonable choosing our systems, and we will define what I mean by that. So the first definition that I introduce is the definition of reference frame. In Newtonian mechanics, a reference frame and sorry, sometimes I abbreviate words like this. This is due to 2 reasons. First, I am very slow writing, and second, sometimes I don't know the spelling in English very well. So I just, it's very nice. I don't need to spell mechanics. I just put mech. dot, and that's it. So in Newtonian mechanics, a reference frame is a choice of origin plus a set of perpendicular, and often we choose right-handed, axes. Or Cartesian axis. In other words, you choose an origin, O, okay? And then right-handed means that you need to choose this like X, this is Y, and this is Z, all right? So this is, let's say, something like this, okay? And sometimes we denote such a reference frame with the letter O. And this O may mean origin, but actually what we mean by it is observer, okay? So we imagine that there is an observer O attached to the origin of their reference frame, and all distances, all locations are measured with respect to O, okay? So O is the person that measures, that tells me distances and distances. Is that okay? Yeah, good. So once we have chosen such a reference frame, and only once we have chosen this, then given such a frame, then we have the position of a particle is then given by a vector r, which is x of t, y of t, z of t, okay? And if you have such a position, then you can define the velocity of the particle, which is the vector with components x dot, y dot, z dot, and the acceleration of a particle, which is as follows. And here, dot means derivative with respect to time, okay? We will also use prime, but that will mean something else in a special relativity. So derivative with respect to time is just this t, okay? Okay, so far so good. And we haven't said anything too drastic, okay? So here comes the first important thing. So let me write it here. So the law of inertia of Newton's first law, inertia, says that there exists a class of frames relative to which the motion of a particle or the motion of a free particle, and a free particle is a particle to which no forces are exerted, right? It's just a particle with no forces, is in a straight line. And at a constant speed. Beautiful. So I would be very glad if you all accept this fact, okay? Now, sometimes people talk about a zeroth law of Newton, and the zeroth law of Newton says that such a thing as a free particle exists. A free particle doesn't exist in the real universe because it would have to be far away, infinitely far away from every interaction. But we can imagine that ideally, if a free particle existed, then there is this class of systems which are called, I will give them a name now, to which that particle moves on a straight line at a constant speed. Okay? So this is an assumption built in our understanding of Newtonian mechanics. And the definition, our definition, another definition, is that a frame in which the law of inertia holds, is called an inertial frame. Okay? So this is an important class of frames, and whenever possible, and always in a special relativity, we will imagine that we will choose inertial frames. Okay? Beautiful. Then, another definition, and sorry about that, we call an inertial coordinate system sometimes ICS, as an inertial frame plus a zero for time. Okay? So you choose when to start counting time. If you make such a choice, together with an inertial coordinate system, this is what we call, together with an inertial frame, that's what we call an inertial coordinate system. Okay? A choice for t equals 0 could be when Jesus was born, and a lot of people like to do that. We could choose something else, and that's also fine. Okay? All of this should be fine. Any questions so far? Very good. So far easy, right? It's, yeah. The cool thing about this course is that today I am going to tell you a lot of things we all agree with, and tomorrow we will see they are not true, some of them. Okay? But so far, it's, people agreed with this for hundreds of years. Beautiful. So in an inertial frame, we also have the second law of Newton, which says that the force exerted to a particle, if it is different from 0, then will produce an acceleration on a particle. Okay? So we already introduced the acceleration. This is force. And the important point is that there is an m in this equation, okay? And this m is what we call the inertial mass of the particle, okay? And an assumption, which we do in Newtonian mechanics, is that this quantity, the inertial mass of a particle, is actually a property of the particle independent on the inertial frame. Or the motion of the particle. Is that okay? So we imagine, let's say, fundamental particles like snooker balls. They have a given mass, and this mass doesn't depend on whether you are still with respect to the table or you are walking with respect to the table. We will measure, or we will say that the particles have the same mass. Is that okay? Yeah? Beautiful. Again, there are philosophical discussions. Some people could say that this equation is empty because it just tells me what the definition of the force is. So this equation makes sense only if you have an independent way of determining what the force is, and then you can use this equation, okay, to compute the acceleration. Beautiful. Any questions so far? Yeah? Do you agree with everything I have said so far? Beautiful. Very nice. So easy so far. Now consider we have two inertial frames, okay? Let me call them O and O prime. And let's say, for simplicity, that they agree on their zero of time, okay? So they are both using the birth of Jesus to measure time, or Donald Trump, or whoever you want to use. And then they say that t is equal to t prime, okay? Now, they look at a particle, at a given particle, and I will say the location of the particle with respect to my system is x of t, y of t, z of t with respect to O, but the other system will describe the same motion as x prime t, y prime t, and z prime t. Okay? Yeah? Very nice. So the first task, which is not super hard, will be to understand how these two things are related, okay, for two inertial frames. Do you prefer if I write here? I guess there is more. Sorry, this is like democracy, but it's, so let me work it out here. So in general, without making any assumptions, for these two particles, for a given particle, sorry, these two descriptions are related as follows. So x, y, z is equal to a given 3 by 3 matrix, x prime, y prime, z prime, plus t, okay? And here, h and t, this is a column vector. That represents translations. So indeed, imagine that O has a system like this, and O prime, let's say, uses something like this. Then this T parameterizes this translation between O and O prime, okay? While H is a 3 by 3 proper orthogonal matrix which represents the rotation of axes. For instance, it could be that this observer is in the United Kingdom, this observer is in Australia, so they will have their axes rotated. And because it's a proper orthogonal matrix, it will satisfy that H transpose H is the same as H transpose, and this is the identity matrix. So this one here means the identity matrix, and is proper, so the determinant of H is equal to 1, where this is really the number 1. Okay? Are you comfortable with this? Thank you. Yeah, because mathematicians will sometimes will not be very happy about this. Beautiful. Now, in principle, these two, H and T, in principle, these two things can be smooth functions of time. Okay? However, by assumption, we are asking for what is the relation between two inertial frames. Okay? So imagine we have a free particle and the system O describes the motion of this free particle. Then because the particle is free, x dot dot, y dot dot, and z dot dot is equal to 0. Okay? However, because also O prime is an inertial frame, the transformation has to be such that this is true if and only if x prime dot dot, y prime dot dot, and z prime dot dot is equal to 0. Okay? Then you can simply take this relation here. You can assume a general transformation, and you can start taking dots on both sides. All right? And you will see that this is true if and only if the only way this can work, so this is true for a general rectilinear trajectory if and only if H dot is equal to 0 and T dot dot is equal to 0. Okay? So that actually means that for the transformation between two inertial frames, the transformation is of this form, but H is a constant and T dot is also a constant. Okay? Yeah? Questions? Oh, sorry, rectilinear. Yes, sorry. Okay, let me rectilinear. It actually, in equations, it basically means this. Now, rectilinear means on a straight line. So you know that a free particle, because of the first law of Newton, a free particle has to move on a straight line. That means rectilinear motion. It's just this. In Latin, rect and straight is the same. So rectus, actually. It also means anus, but okay. But it also means like a straight, something straight, and it's so this is just like a straight line, basically. So the point is that if you have any free particle, the motion of a free particle has to be a straight line, both in the system O and also in the system O prime, because by assumption, both of them are inertial. Okay? And that basically means that if you take this for any generic xt, yt, zt, and you take dot dot on both sides, right? Both sides are equal, provided this is true. Yeah. Yes, you had a question.
So for a free particle, it has acceleration 0.
Yes.
Is there any other condition on a free particle, or is it just
That's fantastic question. No, it's just acceleration 0. Yeah. Yes. However, so there is a physics answer and a math answer. In formulas, acceleration 0 also implies that the particle will move on a straight line. So if you have something rotating at a constant speed, that thing doesn't have 0 acceleration. Okay, so if you look at the trajectory of the moon around Earth, the moon doesn't have 0 acceleration. Okay, so by acceleration, it doesn't necessarily mean that it's moving faster and faster or slower and slower. It just means that x dot dot, y dot dot, z dot dot is actually 0. Yeah, yes.
Is there an assumption here that a free particle in one reference frame is free in another reference frame?
Beautiful, yes. Fantastic, thank you very much. And the reason for this, why this assumption is true, is because I am looking for the transformation between two inertial frames. And by definition, an inertial frame is a frame on which a free particle has no acceleration. Yeah. If you look for a transformation between an inertial frame and another frame which is not inertial, then this wouldn't have to be true for a free particle. So the reason why this is true for a free particle is because we are assuming both O and O prime are both inertial. Okay?
But we also assume that the property of being free is independent of your inertial frame.
That's exactly correct. Yes. And this, yes. Thank you so much for the question. And this is our definition of inertial, basically. So a frame in which the law of inertia holds, that's by definition an inertial frame. Yeah, that's a very important assumption. Very good. Beautiful. Thank you for the questions, actually. I love that. Very nice. So, okay, so if we put this, h constant, t dot equals constant, and in addition, we add the fact that now one of the systems may choose a different origin for time, which is perfectly okay, then we end up, let me write it here, with what we call a Galilean transformation. Okay? So the definition, a Galilean transformation is the general transformation between two inertial frames. Okay? And here we will have our first glimpse of a space-time. Exciting moment for you guys. So if you put x, y, and z together with t, then this, you have 1, 0, 0, 0. This v1, v2, v3. And here is the matrix H, H11, 1, 2, 1, 3, 2, 1, 3, 1, sorry, 2, 2, 3, 2, T prime, X prime, Y prime, Z prime. plus some constant fourth vector. So here, this is a constant vector of length 4. This v is a constant vector of length 3. And H is this 3 by 3 matrix, a constant matrix that we already introduced before. Okay, and they have a name. This T represents translations. This V is called boosts, and this H rotations. Let me explain them nice and easy. So translation, we have already seen what it means. It's just O and O prime could have chosen systems in which O is translated with respect to O prime, okay? But in addition, one could have a velocity with respect to the other, and this is measured by V, by this V, which has kind of the structure of a velocity, and then in addition, H is a rotation of the axis. For instance, if someone is upside down and the other observer is just straight up, then they would have different rotations. Is that okay? So if you write this for generic 1, V1, V2, V3, and rotation H, and a constant vector of length 4, this is called a Galilean transformation, okay? And basically, if you are Galileo, you are Newton, and you have two observers, and these two observers want to translate between one set of information and the other one, they use this Galilean transformation to go from one to the other, okay? So this is the most general transformation that satisfies precisely these relations. So notice that because this T is constant, T dot is constant, you can write it as V times T, so plus another constant, let's say. So this is why we have V1, V2, V3, and T here. Is that okay? Yeah. If it is not, I am very happy to do it more slowly, but yeah. Another thing you can do, you can take this, you can multiply here, and then you can put it in this form and see that H is this H, and then we have this, yeah, where this is V, and then this is the translation. Is that okay? Yeah? Okay. Any questions? Beautiful. Have you seen Galilean transformations before? So you have seen it. You have seen many examples. So for instance, something that you see is transformation of velocities, all right? Like they tell you when they teach you how to drive, if you are driving really fast, you know that actually it is way better to smash against a car going in your same direction than against you, okay? And the reason for that is that in one, you will feel the added speed of both cars, but in the other, the relative speed is what matters. Now, if two systems are describing the motion of a particle, then you need to subtract the speed of the relative speed of one in order to find the speed of with respect to the other one. Is that okay? Yeah. If it is not, please do tell me. You don't feel it's like there are no silly questions. I see some really puzzled faces, so I am. Shall I do this in more detail, or you are happy with it? Yes, what? Don't be shy. It's just more detail. Perfect. Okay. Good. Very nice. So here it comes. Yeah. So if you want. You can decompose these, right? Like here, I don't know, you can call this constant C0, C1, C2, C3, right? Then, for instance, you can see that T, you can multiply here from the right, and you can see that it's a nice exercise that you recover exactly this form, okay? Beautiful. So we have the following now. The two following statements. The nice thing about Galilean transformations is that they preserved Newton's laws. In other words, if the laws of Newton are true in one reference frame, and if you do a Galilean transformation of that, then the laws of Newton will also be true in this other frame related to the first one by these Galilean transformations. Yes? Yes.
Over there in the matrix form, we said that the translation is constant.
Yes.
But over here, we're saying only its derivative is constant.
Sorry, yeah. Indeed. Yeah, thank you very much. So let's do it. Let's do it very, very precisely. So because we said that the derivative is constant, okay, of the translation, then you can always, if you have T dot equal constant, this means that T is linear in time, okay? Because T is linear in time, the way you can write T, which remember in this part of the board, T is a column vector of dimension 3, okay? So because T dot is constant, T itself is linear on time, so we write it as V, a 3 vector, times T, plus a real constant thing, C, that we call 3, right? Where this is C1, C2, C3, and this here is V1, V2, V3. And this V1, V2, V3 is exactly this one here, V1, V2, V3, and this C1, 2, 3 is this one here. And this C0 is this constant here. Yeah, thank you for the question, actually. Yeah. Fantastic. So the first point is that the Galilean transformations, they preserve Newton's laws. So Newton's laws are true in one system, then they will be true in another system if both of them are related by the Galilean transformation. And the important point, and this is called Galilean principle of relativity, and this is the most important part of this lecture, and it's the following. As far as the laws of mechanics are concerned, all inertial frames are on equal footing. This, we take it as granted, but it's an amazing concept, okay? So people got burned for defending this concept, all right? So in particular, it means that we cannot say that an inertial frame is at rest, okay? That is better than another. All inertial frames are equally good. And if you described the laws of nature, you can use, as far as the laws of mechanics are concerned, you can use any inertial frame. Is that okay? And all of them are equivalent. That's why relativity, it has the word relativity on it. All right? Any questions about this? Beautiful. As we will see, and let me spend 1 minute on this. No, I will not. But tomorrow we will see why this is highly non-trivial. And actually, people discussed a lot about this. All right? So basically, humankind, first we thought that Earth was at the center of the universe and was somehow preferred. Then we thought that the sun was the preferred thing, and we could describe things with the sun at rest. Now that we see that not even that is preferred. And actually, all inertial frames, they are all equivalent, okay? And that's an important point. And I think with the years, you are very young, you will see how deep this is. Like if you keep going and thinking about this, you will see how amazing this is. Okay, so in the last 10 minutes, let's discuss the structure of an important thing, Galilean space-time The first definition that I need to introduce is the definition of an event. Okay? An event is something very simple. An event is a specific point in a space at a specific time. Okay? So, it's like saying here and now. Now, if you choose in a given coordinate system, the event, sometimes denoted by E, is labeled by a time t and coordinates x, y, and z. Okay? Now, another system, another frame, will denote this, the same event, by t prime, x prime, y prime, z prime. Sorry. Where the two of these are related by a Galilean transformation. However, we would like to think of the event itself as something independent of any coordinate system. Okay? So if we want to give coordinates to the event, then we need to think of it. We need to choose a frame. It's very much, imagine you have a map, right? And you have a mountain. You think of the mountain independently of the coordinates that you choose to describe points in this map, okay? So we think of the event as something independent of my system that O describes with these coordinates and O prime describes with these coordinates, okay? And here, t, x, y, and z are something fixed. Yeah, so this could be 1 second, and this 1 meter, half a meter, and 2 meters. Beautiful. So now we have the following statements, which are invariant statements. Given two events. And the reason why it's important to understand this is that special relativity will tell us how space and time come together. So let's try to think in Newtonian mechanics. So this, if you have two events, right, there are many things, that are invariant. And for instance, one is the statement A and B are simultaneous, okay? By invariant, I mean that if an inertial frame thinks that A and B are simultaneous, every other inertial frame will agree with that, okay, in Newtonian mechanics, all right? So if two things, look at this, these two things have happened at the same time, okay? And someone on a plane would agree with that, all right? B happens time t after A. This is also a statement that will not depend on your choice of inertial frame. And also, A and B are simultaneous and separated by a distance d. Sorry, I will. Okay? So all these statements are statements that do not depend on the inertial frame that you choose. Oh. Okay, sorry. So one more minute. So we're almost out of time. So let me just end up perhaps with a statement which is not invariant. So for instance, if you have the following statement, A and B happen at the same place, at different times, this is not a very good statement, okay? Because imagine that the first event is this, and the second event is this, okay? We all agree that the two claps happen at the same time, at the same place. However, imagine someone on a plane, right? And that someone on a plane sees me clapping, and then the second time I clapped, I was like 1 kilometer away from the first time I have clapped. So according to that inertial frame, this will not be true, okay? So this statement is not a statement which is invariant under the choice of inertial frame, while these statements are, Okay? Beautiful. So the next, tomorrow, we will continue a little bit and revise some of these other preconceptions, and we will start seeing why in the 22nd century, people started to doubt all this. And then in the third lecture, how Einstein resolved all these problems, and this will lead to a new picture of space-time. Thank you very much, and see you tomorrow.